Hello everyone, welcome to the lecture 10 of course Climate Change and Extreme Events. In the previous week, we have already discussed about what are different climate data type. We have also discussed about different types of data sources. For example, we can work on some satellite data set. We can also work on reanalysis data set. We can also work on climate projections data set. We can also work on observed data set which are measured at the point location. So, and then we have also discussed about what type of uncertainties, errors which are created from multiple different sources and can introduce in these types of data set. So, this is all about the climate. When you are dealing with the climate variabilities, or let's say if you are trying to figure it out, what is the impact of global warming on certain region on different climatological variables, for example rainfall, temperature and all, we look at primarily the observed, reanalysis or different types of data set. These data set can be multiple different types. So, broadly we can divide into two different categories. One is basically called spatial data, where you have one values for different points and then you use some sort of graphical user interface software or MATLAB, Python or R language like that. You try to plot all these values in a spatially distributed manner in order to look at which region has higher rainfall pattern, which region has lower rainfall or drought like condition, which region has a more extreme rainfall condition, therefore can propagate into flooding scenarios like that. Or let's say if you are interested in higher temperature anomaly, which region is experiencing maximum temperature in certain months. So, like that. So, this is kind of a spatially distributed data set. There is another form of the data analysis is called time series data. Time series data you can consider, let's say if you are measuring rainfall at a certain station or place and you are measuring the rainfall for daily frequencies. For example, for different days you have different rainfall values, and then based on the different rainfall values and different days you can prepare a sort of time series information of a particular climatological property of that region. It can be also temperature data, it can also be relative humidity or runoff, or let's say vegetation cover. Lots of data set can be expressed in your time series data set, which basically can define your climatological hydrological properties for one definite time. It could be your daily, or it could be your sub daily, or it could be your monthly scale, or it could be annual scale as well, depending upon your the application area or what you are interested to work on. Therefore, you select that types of time series data set, and therefore you try to understand whether any changes in the time series data or the behavior of climatological properties has been observed in the past record or not. So, this is what we basically make a hypothesis, and based on the data set, observed data set or reanalysis data or satellite data, we try to look at whether my hypothesis is correct or not. So, this is what exactly we use these data set for climatological analysis. In this lecture, we will talk about probability distribution and climate data analysis. When we talk about climate is shifting or there is a change in the climate can be changed into multiple different ways. For example, there might be the possibility of changing the mean or changing the median values of the certain variable of climatological variable, or let's say is there any change in the variability of the system, for example, or is there any change in the overall the distribution of the data set, whether the data set has been shifted towards positive direction, towards the negative direction, like that. So, this figure explains the overall changes in the climate variable at a certain place. For example, it could be location shift in a seasonal minima, or let's say scale shift in the seasonal minima, or let's say shape or minima. And similarly, we can also talk about how the maximum property of a certain region are behaving, whether the location has been changed, whether the scale has been changed, or whether overall shape has been also altered because of the different types of processes which is occurring together at a certain locations like that. So, in order to understand all these processes on these shifts on these behaviors, we look at the probability distribution functions to apply in the climate data analysis. In this lecture particularly, we will talk about the role of probability distributions in the climate data analysis. We will explore some of the common distribution used in the climate studies, and then we will learn how to fit and interpret the distribution in climate data set, and finally we will also talk about distribution analysis to extreme events or something like that. So, this is what the overall agenda of this particular class. So, before moving into the more advanced concept, first we have to discuss about what is exactly probability distribution function. So, probability distribution function is a kind of a statistical function that describes the likelihood of different outcomes in an experiment. Suppose you are tossing a coin, what is the probability of occurrence of tail, or what is the probably occurrence of head at different chances, that is called the probabilities. So, in this case, when you are tossing the coin, it could be either tail or head, which is basically the probability of occurrence is 1 by 2 or 1 by 2. But suppose if you are having a data set a discrete values, and therefore, it can be any value between 0 or 100. So, it could be multiple different probabilities for different which are associated with the different numbers. It is possible that the 10 number are occurring more frequently, and therefore, the probability of occurrence of 10 is relatively higher to any other number. Let us suppose 100 is a very extreme number where the magnitude is very high, but the probability is very low, which means the occurrence of 100 or extreme values are very low compared to your 10 number, for example. So, probability distribution function is a kind of a mathematical representation of values and the likelihood or the probability densities, which is very similar if you plot, let us say, histogram data. Histogram, when you plot, you will get multiple data set, you divide the data into different bins, and then you calculate in that particular bin, let us say 10 and 20, how many numbers are falling, how many times the numbers are falling in that particular range. That is called bins, and the number of occurrences in that bins is called the probability of occurrences of these particular numbers. So, if let us say between 10 and 20 there are 15 numbers falling, and there are total 100 experiment we have done. So, which means the probability of occurrence within the 10 and 20 is 15 by 100. So, similarly, when you make very thin bin sizes of this data set, and instead of calculating the probabilities, you calculate the probability densities of the data set, that will become your probability distribution function. So, it is a kind of a mathematical representation of your likelihood, the probability densities with your corresponding values. So, it also provides or model how the values of random variables are distributed along with different values. So, for example, what is the value for maximum point, what is the value for mean point, what is the value for median point, or let us say what is the probability of occurrence of what is the magnitude of 10th quantile, or let us say 10th percentile, 60th percentile or 90th percentile, like that. So, if you have a mathematical representation of values corresponding to their probabilities of occurrence, you can easily calculate what is the percentile value for 50th percentile, 60th percentile, 90th percentile, 95th percentile, similarly 10th percentile, 5th percentile, 20th percentile, like that. So, probability distribution functions can be defined into can be categorized into multiple different forms. For example, there is a very well known distribution function is called normal distribution, which is a bell shaped curved which is basically widely used for multiple different purposes. It is generally used for symmetric temperature data where we have minus and plus values also. There is a distribution called gamma distribution, where we have captured the variability in precipitation data set. Particularly, there is a distribution function which is called generalized extreme value distribution, which is called GEV distributions. These are the distributions are generally used to model the extreme value events or extreme weather events like floods, droughts, cyclones, like that. Then we have exponential distributions, which are models rare events like droughts and all. We can also apply these types of distribution there. Then we have also Weibull distribution, which is a part of GEV distribution, which is also used for extreme value analysis, extreme value event categorization, or let us say probability understanding of those events, like that. Then we have also generalized Pareto distribution, which is also for analyzing for extreme river discharges or some sort of threshold based analysis. We also use these types of distributions like that. So, this is called some of the probability distribution functions which are generally used in the climate science or allied science of climate, where we use these distributions to basically look into it, what is the probability of occurrence with respect to multiple different values. So, in the climate science, the probability distribution functions basically can summarize the data pattern, what is the trend, what is the central tendency, what is the variability. It can also tell about the statistical properties, or sometimes if you break the data into multiple different data set, we can also understand how the future has been changed because of the changing property of the greenhouse gases or climate change, like that. Using the probability density functions or distribution functions, we can also assess extreme events or extreme magnitude or extreme likelihood of different extreme events with their magnitudes, like that. So, therefore, there is a lots of application in the climate science of the probability distribution functions, starting from the flood risks to rainfall analysis to wind speed analysis to temperature extremes, like that. So, there are so many different analysis we do based on these probability distribution function. So, this is a one example which shows that this is the sort of histogram, and then this is basically a conversion of this histogram into a probability distribution functions. So, here you can see that it has been divided into different bins, and for different bins we have calculated what is the relative frequency or how many times a particular number has been appeared in the data set or time series data set. And this is basically converted into a sort of probability distribution function, where we have it is divided into three parts, where in the middle part is basically called the near near the average value or near the median value, like that. Then this is the part which we call the above average or above normal or above median value, like that. And there is a below, that is a blue color, which shows that what is the values which are below to the certain median threshold. So, this basically the probability distribution functions are divided into three parts, 1 by 3, 1 by 3, it's a equal classes, and the area which are under the each different classes are equal to 0.33 for each different bins. And this figure also explains the slightly shifted lower bins compared to your compared to the higher positive values, like that. When you talk about probability distribution function, when you draw a probability densities like this with respect to their values, it is also important to remember that whatever the area, if you calculate the area of this area under this curve, it will always equal to the 1, because probabilities, if you sum the probabilities of a certain experiment, it will basically always give you a number 1. So, if you think about, let us say you are tossing a coin where you get a head or tail, the probability of occurrence of head is 1 by 5, 1 by 2, and the tail is 1 by 2. If you sum all these two scenarios together, you will always get the probability of 1. So, the maximum sum of the value of probabilities is always equal to 1, and based on that we basically calculate the probabilities of other events, like that. So, there are this is further expansion of the common distribution in the climate data set. We use the normal distribution function, where we it can go to negative direction, or it can go also in the positive direction as well. The property of the normal distribution is kind of a bell curve, where particularly the values are looking, central values are somewhere in this particular example is close to 0, but when you are plotting this normal distribution, it is basically generally defined as a median or mean data set also. So, mean when we do not have a significant shift from the outliers or extreme values, and mean is exactly at the center of median, therefore, mean is equal to median, we can say that. Then is another example is called gamma distribution, which is basically apply when we have extreme values towards the positive direction, and therefore, we fit the gamma distribution function, and then we basically calculate what is the probability of occurrence of different types of events, even the maximum what is the probability of occurrence of rainfall or some meteorological properties in the extreme values or the maximum extreme directions, like that. So, it is a very slightly skewed distribution compared to the normal, where we have the tail of the positive tail is slightly elongated towards the positive direction, which tells that there is some probability is there for extreme values compared to your normal distributions, like that. Then we have sort of exponential distribution, which is also used for extreme value analysis or extreme sort of extreme climate events categorization, droughts and all, where we use multiple different types of these exponential distribution function to calculate what is their probability of occurrence even for the extreme ends, so that we can compare whether the probability of extremes has been increased or decreased or relatively unchanged, like that. Then we have extreme value distribution, which are basically generally used for extreme values. For example, what is the maximum values of temperature in 1 year? If you calculate that, or if you make a time series, then you can use the extreme value distribution to understand what is the frequencies of maximum values for different magnitude in a certain region. Or you can use extreme value distribution for, let us say, flood analysis. You can measure let us say water discharge at a certain point, and for each year you have 365 values, and the 365 values you can convert what is the maximum value, and that maximum value you can select for each different years. You have time series data for a number of different years, and that can be used for this analysis, and you can basically tell whether the behavior of the floods has been changed or remained same or decreased, like that, in the future or historical conditions, like that. So, these are all of the broader categories of different distributions which are used in the climate science. So, let us suppose you have collected the data. So, how do we fit the distribution to the particular data set? Let us suppose we have collected observed data or reanalysis data or satellite data, like that. So, we have gathered the historical data on the particular area of interest where we are collecting the data. Then we have identified, okay, this is the type of the distributions which can be suitable for this particular data set. Let us suppose we are analyzing the temperature data, and there is possibility of the temperature can go in the negative direction also, and the temperature can go in the positive direction also. Therefore, we select that, okay, normal distribution can be the ideal choice where we can fit the data. Let us fit the normal distribution in the data, and then we will find out whether this is the correct representation of the data set or not. So, we identify some of the probability distribution function. Once the function has been identified, we use the parameter estimation technique. So, parameter estimation techniques, for example, when you are saying the mathematical expression of different probability density functions, there is some sort of variables which are there, which basically used by parameter estimation technique, where we basically appropriately choose the best representation of these parameter values, and that we basically used in the different distribution functions. Once the parameter estimation has been quantified, we basically select that specific type of probability distribution function to calculate the probabilities of different events which are occurring in that particular time series data set. This is a general flow of methodologies when we are applying the probability distribution functions in different types of data set. So, once we have already applied the probability distribution function in the time series data set like that, we generally look into it what is exactly the tail behavior, which is basically generally defines what is the behavior towards the tails, positive direction and the negative direction. Positive direction, which means tells about how the data is behaving towards the maximum values, what is the probability of occurrence, and how the data is behaving towards your negative direction, what is the probability of occurrence of the minimum or low values in a certain data set. Then we also look at what is the skewness, whether the data has been positively skewed or negatively skewed, like that. Then we also look at the mean data, or what is the representation of the mean value or central point of a data. It could be mean, it could be median, or it could be mode also in the data set. Then we also look at what is the variance of the data, what is the variability in the data set around the mean or the median, and then we also calculate what is the total variability of the data set. So, these are the some of the properties we calculate once we have already identified the probability distribution function, we have estimated the parameters, and we have specifically identified, okay, this is the probability distribution function which will be suitable for fitting in our data set. Once we have identified that probability distribution function, we calculate these types of different properties, and then basically we apply in different climate analysis. Here, for example, gamma distribution in rainfall analysis, we basically check what is the variability of rainfall pattern, what is the extreme rainfall events, what is their probabilities, like that, what is the consistency of the light rain or the low magnitude rainfall event, and what is the probability of occurrence of the rare heavy rainfall in the data set, like that. So, this is what we basically analyze using the fitted distribution function. So, some of more examples, we can use flood risk assessment using the extreme value distribution function or distribution data set, where basically we use river discharge data to model extreme flood events. We can use the extreme value distribution to estimate what is exactly the return levels or return period for 100-year floods. So, return level magnitude is basically what is the probability of occurrence of 100-year floods. So, 100-year floods generally defines as 1 by 100, which is 0.01 of the probability, and corresponding to 0.01 of the probability, we calculate what is the magnitude using the fitted distribution data set. That is called extreme value analysis, and therefore, we analyze what is the likelihood of occurrences of different extreme flooding events, and based on that information we can inform infrastructure design, dam levy and risk mitigation strategies, like that. Then we can also analyze the heat wave analysis, where we use the Gumbel distribution, and we use different types of different types of distribution function to model the temperature extreme, peak daily temperature or during the heat waves, and then we calculate what is their probabilities, and once we have also established the relationship, we can also calculate what is their return period and their magnitude. Once we have identified the magnitude and return period, we can basically suggest that public health preparedness and urban planning for these extreme events in a certain region, like that. Then we can also include drought duration or drought analysis using the exponential distribution function. We can basically analyze the lengths of dry spells, so different periods where we do not have rainfall at all. So, in that period we basically calculate how many times it has been occurred in the historical period, and then we basically use the extreme exponential distribution data model to fit the data and calculate the probabilities. Once the data has been the model has been fitted, we can identify the pattern of drought occurrences and duration, and based on that frequency and magnitude analysis we can analyze suggest the agricultural planning and water resource management in during the drought conditions, like that. So, in the beginning of the slide we talked about we can fit multiple distribution function to the time series data set, But the question, the one of the very important question is, how do we select which distribution gives us a best result? To answer this question, we can test our different probability distribution function based on different statistical tests. For example, case test or Anderson-Darling test or chi-square test. These tests are basically designed to select or analyze whether the time series dataset we are using and whether we are using the different types of probability distribution functions which are representing our dataset correctly or not. Whether is there any significant discrepancy between your dataset or your probability distribution function, then we can discard that distribution function and then we can select alternative distribution based on these different tests. So, we have the climate data analysis, we assess the distribution fit in the data, we validate our model, and based on that we basically select the improved decision making and calculate what is the climate preparedness for a certain regions like that. So, this is all about probability distribution function and how do we calculate different properties based on the probability distribution function. Once we have calculated the probability, the properties or different metrics based on the probability distribution functions, we can suggest different types of extreme value analysis or extreme climate preparedness or mitigation steps like that. There is one another issue in the time series dataset is called non-stationarity. Non-stationarity is basically defined as, let's say, in the time series dataset, in a certain point after because of some influence externally or some internal process or some change in the process of behavior, the time series behavior has been significantly changed from the historical period, which means the statistical properties of the historical period does not give any similarity with the present condition of the data set. When there is a change in the statistical behavior or change in the process of your certain climate variables like that, that is called a non-stationarity in the data set, which can be originated from the mean, change of the mean or variance, or overall the change in the distribution of the function over the time. So, for example, if you are talking about long term trends in certain meteorological parameter because of the global warming, that is also gives you an idea about there is a non-stationarity there in the data set. Or let us say there is a changing in the variability, which also suggests that there is a more frequent or intense extreme weather events compared to your historical period, and which basically suggests that the statistical property has been already altered or already changed. So, basically these are the different processes which can lead to change in the climate time series data set. For example, long term spells or the changing the rainfall pattern, then global warming, then basically let us say the drought conditions or different types of extreme hydrological events, or let us say there are multiple external indicators, for example sea level rise or temperature rise of sea surface temperatures like that. So, these different types of parameters or processes can exaggerate this non-stationarity conditions in the data set. Primarily you can divide, you can understand that there is a natural variability and there is an anthropogenic variability which can change the behavior of the data set. So, once you know that okay, there is a non-stationarity in the data set, these non-stationarity you can sense if there is any trend in the data, or if there is any breakpoint in the data, or is there any sudden change in the statistical behavior in the data set, that basically called the non-stationarity conditions of the data. So, how do we handle the non-stationarity in the data set? We can use the dynamic models, time varying coefficient models, or we can use the spatial temporal models or regional trend or seasonal pattern, we can decompose that, or we can focus on the extreme events or applying the peak over threshold methods or threshold selection methods to basically remove the non-stationarity conditions in the data set. If we still have the non-stationarity, we use the some sort of time varying coefficient or dynamic models to capture the non-stationary behavior in the data set. So basically the primary steps are, we have to detrend the data, we have to remove the linear trends in the data set or making it the data as a stationary data. Then we have to also capture the climate trends. If there is trends, we have to detrend that data from trend from the data set. And then we can also use time varying parameter. For example, in the initially we talked about, when we are identifying the probability distribution function, we identify the parameters. So essentially those parameters are constant in the nature. But if we also consider, let's say, those parameters is the function of time, that can also be evolved through time, and that can be considered as the time varying parameters for a different probability distribution functions. So this way we have to remove, we can remove the, or we can deal with the non-stationarity conditions, and then we can use different probability distribution functions which are meant for stationary analysis, or if there are specific types of probability distribution functions which are having component of time varying coefficient change, can also be used in the stationarity, non-stationarity assessment of different types of data set like that. So we can use multiple different tools, softwares to analyze these types of extreme value analysis, or for example probability distribution function analysis like that. We can use Python, we can use R libraries. For example, these are the libraries, we can use it for visualizing or analyzing the distribution or fitting the distribution in the data set. We can use the easy fit or MATLAB or SAS software also, which can also be useful or analyzing the distribution in the data set, and then we can also generate more informed results based on their different properties. So in this lecture we have talked about what is exactly probability distribution functions. We have talked about what is their fundamental analysis in the climate data, variables or different types of variables in the climate data analysis. Then we have also talked about how do we fit the distribution which requires careful parameter estimations and testing. Then we have also talked about various different applications, including understanding of extremes or supporting of climate resilience and planning, which is basically used based on fitted the distribution function in your time series data set. We have also talked about the non-stationarity conditions, and how if there is a data set which has the non-stationarity conditions, we can detrend the data, or we can remove the trend from the data set or the non-stationary behavior from the data set, and then we can use it for multiple different purposes like that. So this is for overall for this particular lecture. In the next lecture we will primarily talk about introduction to the extreme value theory and its application in different types of climate analysis like that. Thank you so much for your attention.